So thanks very much for the opportunity to present, and thanks also to Elder for setting the scene in terms of internal waves and other bits of oceanography that I won't dig into in any detail. So this is a presentation funded as part of a NERC project through the CLASS program, which involves a number of collaborators and different organizations who are referenced here. And I guess the kind of headline thing is it's not going to be a surprise. I've kind of ruined that for you. So at the beginning, I want to talk about the motivation for this study, and this is particularly thinking about, we understand that submarine canyons and submarine channels are globally important conduits for particulate transport, and that includes sediments over longer periods of time and potentially pollutants and organic carbon over shorter periods of time. But the existing paradigm suggests that most of the canyons around the world that are active in the present day are those which have a close connection to shore. So either are fed by river systems or intersect littoral cells where a long shelf transport provides that sediment. And that accounts for maybe 25% of canyons worldwide or thereabouts. And the remaining 3/4 of the 9,000 submarine canyons worldwide are disconnected from present-day sediment input sources. So the paradigm, and taking this example, this nice cartoon from Jake Koval's 2010 paper, suggests that canyons that are extremely disconnected by maybe tens or hundreds of kilometers from present-day coastlines are likely to be inactive in terms of turbidity current activity. Now, it's been possible to start to test aspects of this, particularly in land-detached canyons, so those which connect close to river sources or intersect littoral cells, using advances in direct monitoring technology. And Peter Talling, Meg Baker, Sean Ruffle talked about this on day one of this conference. And we can use sensors like acoustic Doppler current profilers to actually look inside the internal structure of turbidity currents, identify when they occur, how frequent they are, how long, how fast, potentially what triggered them. And so these advances in technology have really spawned. Okay, so these advances in technology have really been tested, first of all, in systems which have extremely close connection between river systems. So examples like John Hughes Clark has shown from the Squamish Delta in Canada, Kim Conway and others in Butte Inlet, where you can maybe have many tens or hundreds of turbidity currents in a given season. Peter Talling showed 2 days ago how submarine canyon systems that have a very close connection, in this case in the Congo Canyon, the head of the canyon goes 40 kilometers up the estuary itself. There's a direct connection, and we don't necessarily need rivers to directly feed in if there's a significant amount of sediment being fed in through littoral transport. So Charlie Paul at Mbari and others have shown how systems such as the Monterey Canyon in California, and indeed other canyons on the California borderland, can be extremely active. However, there's a very strong bias towards submarine canyons that are land attached. This is where we've been expecting turbidity currents, so this is where we have gone to measure turbidity currents. And there's been a lack of direct measurements in land detached submarine canyons, which means that aspect of the existing paradigm that land attached submarine canyons are switched off with respect to turbidity currents in the present day highstand remains untested. So that was really the motivator for this study. So I'm going to take you to the Northeast Atlantic here, to the land-detached Whittard Canyon. It's a complex canyon. It's kind of got this branching dendritic morphology. I'm going to go to the upper part of the eastern branch of the Whittard Canyon, whose head lies about 300 kilometers from the nearest coastline. I mean, as part of this experiment, over about a 50-kilometer length of the canyon from its head, we deployed 2 moorings. One mooring M1 at 1,500 meters water depth, which has a high frequency 600 kilohertz ADCP looking downwards, so we get 1 meter vertical resolution of velocity and information on sediment concentration. And then at 2,000 meters water depth, an upward looking ADCP with a 75 kilohertz ADCP. So lower resolution, maybe 8 meter bin sizes, And the first measurement that we make is almost 40 meters above the bed. So in contrast to 1500 meters, where we're measuring down to about 2 or 3 meters above the bed, here we probably only get the first measurement about 40 meters above the bed. So we're only going to catch flows that are thicker than that. So here's just an overview of some of the data. This is a year's worth of time series from that M1 mooring at 1500 meters water depth. And this is work that Ewan Sutter at Manchester is working on at the moment. And this is the bin that's closest to sea floor, so about 2 or 3 meters above the seabed. And hopefully what you can work out if we just zoom in on a section here over a few days is we see this tidal frequency signature. So these are internal waves that are moving up and down the canyon on a tidal frequency. And then we also start to see these spring neap tidal cycles as well. And coincident with these up and down canyon tidal cycles of these near-bed flows that reach in some cases or exceed a meter per second. As we get higher velocities, we get a higher echo intensity, so more backscatter coming from the instrument and the bin near seabed. And this is a proxy for suspended sediment concentration. And particularly around spring tides, we're seeing enhanced suspended sediment concentration. It's probably no surprise that these almost a meter per second flows are capable of suspending or resuspending sediment, which is typically kind of fine sand at seabed. But one of the other surprises, aside from just quite how vigorous background internal tides are, was when we recovered the sediment trap on this mooring at 1500 meters water depth that was located 10 meters above the seabed. We found that not only the first bottle had filled up, and this first bottle was designed to capture just the first 8 days of measurements. The bottle was full up, but so was the sediment trap, almost entirely to the brim. And it was full up with sediment. Here we show the grain size distribution in grey from the funnel and in black from the bottle at the base of that sediment trap. So this is 10 meters above the seabed. We find that the median grain size is between about 110 and about 150 microns. So fine to medium sand is being suspended at least 10 meters above the bed. That was one surprise. The second surprise, and probably the bigger one, was that during a period of 12 months, we captured 6 powerful turbidity currents in just that 1 year alone. We can look at velocity profiles through these flows, and we see velocity structures pretty diagnostic of kind of textbook laboratory type turbidity currents. They lasted several hours in duration. This is color coded by down canyon velocity, the hottest colors. So these are flows that were net down canyon. They show a sudden increase in velocity, which tails off. In some cases, they have a couple of pulses or peaks to them. And the measured velocities from the ADCPs are up to about 5 meters per second near bed here, maybe even just a little bit higher. We also recorded 3 of these flows at the mooring at 2000 meters water depth, so potentially traveled for 50 kilometers and even longer. And looking at the transit velocities, we determined speeds potentially up to 8 meters per second. And typically ADCPs under-record the measured velocities, so this makes sense, but depending on the travel path that we estimate, this varies, but potentially speeds of up to kind of 3 to 8 meters per second for these flows. So if you take nothing else from this presentation, for us, this was a surprise, maybe not for others, but a remarkably similar frequency and magnitude of flows to other land-attached submarine canyons, but this is for a land-detached canyon. So if we compare the frequency and the speed of the flows to other major systems such as the Congo Canyon, to Monterey Canyon, to Nazare, also in the Atlantic, but that cuts very close to shore, other canyons of the California borderland, the Galpin Canyon in Taiwan, a very, very similar pattern seems to appear. Precisely what triggers these flows remains still quite unclear. There's certainly no consistent triggering mechanism that we identify. We can look at meteorological and oceanographic conditions from ADCPs and also from Met Office buoys that we have nearby. And we find that when we look at wave height and air pressure as a proxy for storms, there's no consistent link here. And certainly, actually, we find that most of the turbidity currents are occurring during the spring and the summer period. We can't do statistics with n equals 6, but we're finding that you don't need big storms to create these flows, and indeed most of them happening during the spring and the summer. And this is interesting because the head of the canyon features phytoplankton blooms, which provide significant amounts of fresh organic carbon. So it's possible that these flows are very capable as being agents of efficiently transferring this fresh organic carbon further down and into the deep sea and sustaining some of the important deep sea ecology. So we come to the conclusion that we can't make an obvious conclusion about the trigger.
2 minutes,
We've looked at these vigorous internal tides to see whether there's any correlation between whether we have spring or neap, whether we have upgoing or down canyon tides, whether it coincides with the surface tidal regime. And again, there's no consistent pattern here. It's a little bit of everything. There's no link with earthquakes apparently within a 1,000-kilometer radius of the head of the canyon, nor necessarily with fishing activity, although this is something we're going to investigate with field measurements. So looking at dredging and bottom trawling, there seems to be no obvious link. But this at least is reassuring because land-attached systems, either fed by littoral transport, such as the Monterey Canyon, by bedload-dominated transport from rivers or from the Congo River to the canyon. Lewis Bailey has previously shown in a paper published last year that there's also no consistent or obvious trigger for some of these other systems. You don't need large external events for turbidity current inception, even powerful flows. But what you do need is, if you have these clustered, temporally clustered flows, they tend to relate to seasonal enhancements in sediment transport. Here, actually, sediment transport on the shelf appears to be enhanced during the autumn and winter when we get stormy period. But it looks like that the direction of sediment transport towards the head of the canyon is preferentially happening in the spring and the summer, whereas in the autumn and the winter, those big storms drive sediment away from the head of the canyon. But again, this is something for us to explore in some more detail, and we're doing some field work out in the canyon to do repeat surveys towards the end of this summer. Is it just Whittard Canyon that's like this? I think it's probably not, but this is certainly a hypothesis to test. Work on submarine canyons, looking at repeat time-lapse bathymetric surveys in the South China Sea, looking at the transport of litter within canyons in the South China Sea, both of which are extremely disconnected from present-day sediment input sources, suggests that we might also have a similar sort of activity. And indeed, work off Northwest Australia, looking at repeat surveys published earlier this year, seems to also suggest that other land-detached canyons may also be active with changes diagnostic of turbidity current activity. So closing and providing a kind of, I guess, a testable hypothesis, I think potentially we have underestimated the particulate flux along land-detached submarine canyons in the present day. We suggest that there's probably about 1,000 or just over that similar submarine canyons to Whittard Canyon in a similar sort of configuration. And it's entirely plausible that those systems may also be similarly active. So thank you for your time, and hopefully there's some food for thought.
Thank you, Mike. That's definitely food for thought. Put your questions in the question box or in the chat for Mike. Short question while those come in from me is what is the composition of this sand in the turbidity currents in the trap? Mineralogy, and what is its provenance? Where do you think it's coming from?
It's a good question. It's a bit of a mixture. We haven't done much detailed work on it. It's dominantly quartz. There's a bit of other material in there as well, but I guess when we talk about sediment supply, there's probably not a huge amount of sediment being supplied in the present day, but the last glaciation saw retreat of large river systems that came through, the whole area to the northeast. So it left a huge amount of sediment stock. So the fuel is there for it. So if there are other systems that have previously been glaciated, have broad shelves, and have previously had large sediment supplies, that legacy remains potentially for a long period of time through to the present day highstand. So there's a bit of reworking. There's certainly some evidence from repeat surveys that Claudio Loiacano presented on an EPSL a couple of years ago that suggest that you have unidirectional bedform fields at the head of the canyon. So it looks like there's active sediment transport there. It'd just be interesting to explore other systems and see whether Whittard's indeed unique, or whether there are other, other analogs.
Cool. Okay, looking very much to evolving that. Do put your questions to Mike in the chat, and we will move on to the next presenter.